this episode, we're going to talk about a security idea that sounds fancy at first, but becomes very practical once you connect it to a simple goal. Don't let systems quietly change underneath you. Attackers love persistence, which means they want a way to keep access even after you fix the original problem, and they often achieve that by changing a running system in subtle ways. Immutable infrastructure is a pattern that fights this by treating deployed compute as something you replace rather than something you constantly modify in place. Instead of logging into servers and making manual changes, you rebuild a clean version from a trusted image and redeploy it, which makes hidden attacker changes much harder to keep alive. The big benefit is that it shrinks the time window in which a compromised system can remain quietly compromised, because systems are refreshed and replaced more predictably. By the end, you should understand what immutable infrastructure means, why it reduces persistence risk, and how it connects to hardening, patch cadence, and monitoring. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To understand immutability, start with the everyday meaning of the word immutable. It does not change. In infrastructure terms, that does not mean your environment never changes, because environments always evolve. It means the way you apply change is different. Instead of changing a running server repeatedly over its lifetime, you define what the server should look like in a build process, create a new version, and then replace old instances with new ones. If you need to update software, you build a new image or package, deploy new instances, and retire the old ones. If you need to change configuration, you update the source of truth for configuration and redeploy rather than editing configuration directly on the running system. This is a mindset shift. Deployed compute becomes more like a disposable appliance and less like a pet you nurse for years. That shift is powerful for security because it reduces the opportunity for unnoticed drift and long-lived compromise. Persistence is the enemy here, so it helps to be clear about what persistent compromise looks like. Attackers who gain access often try to plant something that survives reboots, password changes, or even partial cleanup. They might add hidden user accounts, modify startup processes, install backdoors, or adjust firewall rules to keep a quiet channel open. In cloud environments, persistence can also involve adding new access keys, modifying roles, or changing automation scripts that will recreate attacker access later. The common theme is unauthorized change that remains in place over time. If your infrastructure pattern encourages frequent manual changes on running systems, it becomes difficult to tell which changes were legitimate and which were attacker actions. Immutable patterns reduce that ambiguity by making the expected state tightly controlled and by limiting the number of ways the running system can be modified. One of the biggest security benefits of immutability is reduced configuration drift. Drift is what happens when systems that are supposed to be identical gradually become different, often because of manual fixes, emergency patches, or one-off configuration edits. Drift makes monitoring harder because you can no longer assume that a baseline applies to every instance. It also makes incident response harder because you cannot quickly determine whether unusual behavior is due to compromise or simply due to a weird configuration difference. Attackers benefit from drift because it creates fog, and fog makes it easier to hide. Immutable infrastructure fights drift by making replacement the normal way to introduce change. When every instance is created from the same trusted build process, differences become less common and more meaningful when they appear. Immutability also supports faster recovery because replacing a system can be simpler than repairing it. If you suspect a system is compromised, you can remove it from service and replace it with a clean instance built from a known good source. That does not solve every problem, because you still need to investigate how compromise occurred, but it reduces the risk that the compromised system remains active. It also helps prevent the common mistake of trying to clean a compromised system and missing a hidden persistence mechanism. Attackers are skilled at hiding, and cleanup under pressure is hard. Replacement is often safer because it restores a known baseline without needing perfect forensic certainty about every change made by the attacker. In this way, immutability shrinks the window of opportunity for the attacker to maintain a foothold. This pattern connects directly to hardened images because immutability depends on having a trustworthy source for what you deploy. If your images are outdated or insecure, replacing systems frequently does not help much because you are repeatedly deploying weakness. That is why secure compute deployment and immutable infrastructure are partners. Hardened images create a safer baseline. Patch cadence keeps that baseline current, and immutability ensures that running systems reflect the baseline rather than diverging from it over time. When these practices work together, your environment stays closer to what you intended, and that reduces both attack surface and uncertainty. Beginners sometimes treat these as separate concepts, but in practice they reinforce each other. The tighter the relationship between build and deploy, the more predictable your security posture becomes. Immutable patterns also change the way you think about administrative access. If your normal workflow does not involve logging into servers to tweak settings, then the pathways for interactive administration become less necessary. Fewer administrative pathways means fewer opportunities for attackers to use stolen credentials to manipulate running systems. It also reduces the temptation to make quick manual changes that are not tracked properly. In an immutable mindset, changes should go through a controlled process that produces a new deployable artifact, such as an updated image or configuration package. That process creates natural auditability, because changes are recorded at the source rather than scattered across running instances. Attackers often exploit environments where changes happen informally, because informal changes are hard to distinguish from malicious ones. Monitoring becomes more effective in an immutable environment because expectations are clearer. If instances are meant to be identical and short-lived, then unexpected changes become strong signals. For example, if a workload starts running a new service that was not part of the image, that deviation is suspicious. If a system's configuration differs from the declared baseline, that could indicate unauthorized modification or a broken deployment process. Immutable environments allow you to focus monitoring on deviations from the known build, because those deviations are less likely to be benign. This does not eliminate the need for logging and investigation, but it increases signal quality. A stable baseline is like a clean sheet of paper, making new marks easier to spot. However, it is important to address a common misconception. Immutable infrastructure does not mean you never store data on compute. Applications often need to handle data, but the pattern encourages separating data from the compute instance's local state. If data is stored only on a single instance, replacing that instance becomes risky and disruptive. A more resilient design keeps persistent data in dedicated storage services, while compute instances remain stateless or nearly stateless. That separation makes replacement safer and faster, which is essential to shrinking the compromise window. Attackers often target local state because it can contain secrets or configuration that grants access. When local state is minimized and secrets are managed carefully, attackers have fewer durable places to hide persistence. Another subtle benefit of immutable patterns is that they encourage disciplined patching and updates. If you know that updating means building a new version and redeploying, you naturally create a rhythm around releases. That rhythm can be aligned with patch cadence, making it easier to keep systems current. Instead of worrying about how to patch hundreds of running instances individually, you patch the source image and then roll out new instances. This approach does not remove all complexity, but it reduces the chance that some instances remain unpatched because they were forgotten or treated as special cases. Attackers thrive on forgotten systems, so consistency is a defensive advantage. Over time, the practice of frequent replacement becomes a built-in hygiene mechanism. Immutable infrastructure also helps with containment during incidents because it supports rapid removal of suspicious systems. If monitoring flags a workload as possibly compromised, you can isolate it, capture needed evidence, and then replace it. This prevents a compromised system from continuing to interact with internal services while the investigation proceeds. It also reduces the risk of an attacker maintaining long-term persistence on that instance. Of course, you still need to address the root cause, such as stolen credentials or misconfigurations. Otherwise, the attacker may compromise new instances as well. But removing compromised compute quickly narrows the attacker's options. The shorter their time inside, the fewer opportunities they have to expand their influence. There are trade-offs and limits, and it is important for beginners to recognize them. Not every workload can be perfectly immutable, especially legacy systems that rely on local state or manual operational changes. Some environments also require emergency fixes that may not fit neatly into a rebuild and replace cycle. Even so, the principle can still be applied by minimizing in-place changes and by ensuring that any necessary changes are captured back into the build process quickly. The pattern is less about achieving purity and more about reducing unmanaged change over time. Every step toward more predictable rebuilds and fewer manual edits reduces attack surface and improves investigative clarity. The aim is a direction, not an all-or-nothing switch. To wrap up, immutable infrastructure patterns shrink the window for persistent compromise by making systems replaceable and predictable rather than long-lived and manually modified. When compute is treated as disposable, unauthorized changes become harder for attackers to maintain and easier for defenders to detect. This pattern reduces drift, improves monitoring signal quality, and supports faster recovery because replacement restores a known baseline. It also reinforces secure compute deployment practices like hardened images, reduced services, and consistent patch cadence, because those practices define what the baseline should be. Immutability does not eliminate all security risks, but it removes a major advantage attackers rely on, which is the ability to quietly change a system and keep those changes alive. With that foundation, it becomes easier to validate compute security continuously, because you have a clear baseline to compare against and a clear process for keeping systems aligned with it.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.